it. So problem 4. Okay. So I'll break down the question into simpler parts and then I'll ask people what they have tried and so on. Okay. So I have intentionally not stated the question very syntactically precisely. Okay. But let's see. So we have a subset of R. Okay. And it has the following properties. A has arbitrarily small positive elements, number one. Okay. And number two, A has arbitrarily large sum. Okay. So now with this itself, the question is A dense in R? Okay, not A, I'm sorry. So with this, now we are asking that if you take kind of the arithmetic generated by A, or I should just maybe say the just the vector space or whatever generated by A, you can, okay, not vector space either. Okay, just that if we take all elements of A and we take all possible finite summations of the elements of A, and also, okay, just let's just take finite summations for the time being. Okay, so for example, if A was, in case the question is not clear to someone, if A was, let's say, like this, which may not be it is not general enough because sometimes A may not be countable and so you can't list it, but just saying, okay, A was like this, then your A comma plus would be, x1 plus x2, you have x2 plus x3 plus x4, all finite sums you are allowed to take. So it's a different set. Okay, it's a different set, and it is not, you cannot say this is a vector space over R. Okay, you could say that you can call this vector space generated by A over natural numbers in some sense, right? Because you're allowed to take 2x1, for example, but you're not allowed to take pi x1 if pi is not in the set, right? 2x1 comes naturally because you will basically be adding, right? So this is also called the monoid generated, but doesn't matter, that words are not important. So we are asking, the question is that is A dense in R? Is A, so this is my own question that I just I made for some other student a while back. So is A dense, because actually I was, yeah, I'll tell you later, that is A dense in R. No, Anish, it's not an abelian group because I'm not taking subtractions. I'm not subtracting, in the sense I'm not taking additive inverses. So it's not an abelian group. Okay. Yes. So in that sense, even this doesn't make too much sense when I say over, it's not even a vector space then, because I'm not allowed to take negative. But anyways, that's in some sense is but yeah, it's a monoid generated by A. You can, it's the precise word, or rather semi-group is better because there may be no identity. But anyways, yeah. And if this conditions are not clear, because I've intentionally left them like this, because this is a language in which is used heavily in later on in maths. So I've left the conditions like this. If someone is not clear, then you can please clarify that. Acha, Noel, can you explain us what these two conditions mean? Can you state them more mathematically? Okay, it will also help you to think, if you state them clearly.
So
Mhm.
What I'm to say is what these two sentences will combine, amplify, or
No, like what does the first sentence mean mathematically? Because I've just said arbitrarily small, but what
yeah.
does it
So
mean?
yeah, so we can choose. That's the meaning. So we can choose the smallness. One can say that.
Yes, yeah. So I'll just write it. Yeah, you're correct. So given any epsilon bigger than 0, there exists a x in A such that x is less than epsilon. And of course, x is positive, so that's important.
Yeah.
So this is the sense that it has very small elements also. Okay. And the second condition is saying that it has arbitrarily large sum, which means that
Okay.
given, so yeah, can you describe that? Given any m bigger than 0, there exists x1 only finitely many. This is very important. Okay.
Yeah.
There exists some things like this such that x1 x2 till xn.
So one thing in A plus, we are taking all possible combinations of additions of elements or what?
Yes, that's right, that is exactly but only additions. You're not allowed to take subtractions in this problem, in this
Yeah,
part.
yeah, that's clear.
Okay,
Yeah.
yeah, that's why it's not like a Boolean group. Okay, because there you will have negative also. Okay, so see why. So the intuition I think why I think or thought it is true when I was making the question is because see, it has very small things, right? So it's very close to 0. There are a lot of things in A, and then there are very big things also. So I'm saying that you can somehow the feeling is that you can reach anywhere by first taking the big steps and reaching close, and then using these small things to get that the final touch. Okay, to get close. That was the intuition behind making this, but we'll see if that is sufficient or not. Mhm. Maybe, but this is not a subgroup. So this is a problem with this question. It's not a conventional question, I will say. I mean, at least, yeah. So it's not a subgroup. So the problem is that if you take the minimum positive element, um, if you take the minimum positive element, then how will you get a smaller one, right? Uh, mm, okay, so let's see if we can extend that argument. So he's saying that try to use the proof that is used to show that any subgroup is either dense or an arithmetic progression. Okay. So if you no, but I mean that will only prove that it is dense around 0, right? Or will it prove? Hmm, yeah. So I guess his reasoning makes sense. Yeah. So yes. So try to use the group thing. Try to So this is not a group, okay, but because it has arbitrarily small things, try to use the proof that is used to show that a subgroup is either dense or an arithmetic progression. So see, it is certainly dense around 0, right? That's what the statement is saying. Okay, it is dense around 0. Yeah, so this, yeah, okay, right. That's a good reasoning. Yes. So I guess the answer is yes, right? It's very clear that the answer is yes. So it's not even a difficult question, though I've slightly incompletely stated it. I'll make it harder just in a minute. So let's say you want to get to some number t. So how can you get it? By taking additions in A. So I mean, obviously, I also need a epsilon neighborhood, and you want to land in this.
So property 2 can help here,
Okay, property 2.
being having a large sum.
But yeah, okay. Having a large sum, but what if t is like 1.2? Let's say t is
Then
1 point.
property means
Huh,
help of
yeah, okay, okay, yeah. Um, hmm. Oh, but you don't even need property 2 in this actually, right? Because think like if you have epsilon here, and then you can just choose something which is less than epsilon, right? You can choose a x1 in A, which is less than epsilon. Now, if you just take jumps of size x1, and you'll reach where you want to reach, right? You have x1, you get 2x1, right? 3x1, 4x1, 5x1. I mean, at a certain point, you will end up in this, right? Because this is a gap of size 2 epsilon. You can't really jump out. You can't skip it. If you start with x1 which is less than epsilon,
yeah. If we take x1 to be less than epsilon, yeah, that is correct.
you can repeat it and reach there. So this is in fact a very trivial question in that sense. You don't even need the second condition. Okay, right? So yes, so that was that's like a question, failure question. It's a failed question. I have failed it. I have failed you people as okay on this, but I will. But it's not what I actually intended. So yeah, I messed it up while defining. So here I will say I will add a condition: distinct finite summations, or I should say summations with distinct summands. Finite. Now it becomes even more combinatorial, okay? Because I mean, now it's not an algebraic structure, right? It's very weird. Finite summations with distinct summands. Now you will need to use the second condition to get close, if this is true at all. Yeah. So does everybody see how this makes it different? Basically, I want to nullify the effect of taking something again and again, because that's really making this problem trivial. Okay. So at this point, it is just so 2x1 is not allowed unless 2x1 is already there in A. That then of course it's there. So you can take x1, you can take x1 plus x2, x1 plus x3, but not x1 plus x1. Okay. So yeah, now the second condition you will be needed because the small guys may not be able to go there. Okay. So so yeah, what do people think about this? What is their intuition saying? Yes, Noel, what do you think? Will this be true?
Yes, sir. Yes, sir.
You think it is true? Okay. I
So
also think
we can
that.
we
Yeah.
can take we can go to any real number r that is true, right?
How do you prove
Uh,
that?
from the set, right?
How?
We just prove that.
No, but that was a different. That was slightly different. There, we were not there. We were allowed to take multiples of the same number, of the same element. Here, we are only allowed to take finite summations.
Okay, 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 okay,
So
okay.
now this question is more combinatorial. I mean, in the sense that it is not an algebraic structure now. A semi-group
Yeah.
monoid, it is nothing because in any of them you're allowed to. So you're not allowed to operate the element with itself. Okay, so it's a new operation where x1 plus x1 is 0, let's say. Okay, yeah. So yeah, then yeah. So then the feeling is that you can use the m you can use the m to go very close to go like to take the chunks, to take the big leaps and go close, go, and then maybe use the small ones to do the fine touches in the end. That was the basis on which I made the question. Okay, but do you think you can always do this, or can you find a counterexample? So the counterexample meaning you have to think of a set which has these two properties, which has big things and very small things. Just think like that, yeah. But you still can't get everywhere.
What about one by two square, one by three square, so on? That's it.
1 by 2 square, 1 by 3 square, and so on. No, but the problem with this is, Noel, that this
Yeah, yeah.
doesn't have
I
the second.
understand.
Yeah.
Yeah, second one is not followed. I am just improvising on this.
Yeah, but I think you can improvise on this and make it work. You have to just add something in this, I guess. This will take care of the first condition. Yes, Anish, what do you think? Or yeah, if anyone can say. Okay, okay. Try to not think too mathematically. Like, don't try to think of any theorem. This is like a, it's a little, yeah, that kind of unconventional question. Yeah. See, this is one general thing is there, right? Even if you look at the inclusion exclusion principle, right? I mean, to really get to something, even if you add something to get to something, you have to do some kind of approximation. You have to go up and down. This is only going up, right? So in most cases, this kind of things will never be dense. Okay. Uh, yeah. So yes, I mean just throw in some big elements in this, right? Just throw 100, 200, and so on, right? Then how are you going to reach the number 10? You won't reach. Simple. It's just that simple. This is this is good, but it only has some finite power. And if you're not going to subtract also, then how are you going to come back? So yeah, you will not get it. You will not get to number 10, for example, right? If you take this set. Yeah, so these two conditions are quite different. And so they don't add power to each other. You see, in that sense, yeah. So this is not true. Yeah, not true. So initially I was desperate to make a question, so I made it. Then I realized after making it that it's not true. Okay. Um, is that okay, Noel? Yeah, is it clear? I guess it's clear.
Yes.
Yeah, it's in fact very simple. I think we were just thinking too mathematically. Yeah. So now then I tried to update the question. Okay. So I updated it with, so again we'll only take distinct summands because we realize that if you take repeated, then as Anish pointed out in initially that you can just get anywhere close to anything because you can just take epsilon and so on. Now I am allowing subtractions, but of course, yeah, don't subtract anything two times, something like that. Okay. So maybe this is basically a monoid in which the operation is that x plus x is 0 and minus x is, as a consequence, also 0. Okay. This is the for any x. Other than that, it's just natural addition. So okay, so you're allowed to do things like this: x2 minus x3 plus x4, and even things like this. But as you remember, this is not the right way to write it because this may be an uncountable set. Okay. Yeah, but then yeah, for uncountable set, something happens very naturally. The sum becomes unbounded, but that is not easy to prove. That will not go into right now. So yeah, it's okay to do this. So now again, the question is this dense? Because now you have a chance to come back. Is this dense in R? So through these problems, the goal is to develop intuition about denseness. Because I could have done a lot of hi-fi things maybe. I could have seen and shown and so on. But yeah, I want to develop the intuition, you know, so that when you can't use a theorem, then also can you think? Because of course, yeah. And if someone is not getting an intuition for this, then just try to take the example that Noel started to construct, and what I added to that. Basically, what I added was not is just anything will almost anything will work. And just think if in this example this is working or not. You can try that. Is it becoming dense or not? I'll be back in 30 seconds, okay? Just keep this think. Yes. So yeah, so can we just check that it works or not in this? Right? That we can check, right? So basically, just can you reach the number 10 using these things?
No,
Huh?
no.
No. So then the answer is no, right? Simply, right? So yeah, the reason why I'm doing these questions is because these are unconventional questions, and so you're forced to think about them, right? Otherwise, you just use some theorems and such, or some analytic argument. These are not even analytic; these are like stupid questions. If you ask some analysis person, they will say, "What kind of questions are these?" Okay, but yes, so you can't reach here, right? There's really no power. Yeah. So now my question is, after all this, what intuition have you gained? The problem is that even though this has arbitrarily small things, but these things which are arbitrarily small don't have sufficient power, right? Don't have sufficient power. That is one of the problems. If they had sufficient power, in the sense that if even though they were arbitrarily small, but even if the sum was infinite, then you could maybe use addition and subtraction to reach anywhere, right? But they don't have enough power, so after you go to 100 you can't come back, because these small things are small, but then their sum is also small. Okay, if the sum was infinite, something like that, then you could have reached close to 10. Okay, as close as you wanted. So with that being the idea, how should I modify the question so that it does become dense? Okay, so So the modification that I was thinking of is that there is a part of A, okay, there is a part of A such that summation A is unbounded, meaning basically arbitrary last sum. And then there's another part, B1, whose summation is also unbounded, okay, also unbounded. Um, Unbounded. But A1 and B1 have arbitrarily small elements. Okay, A1 and B1 have arbitrarily small. So I am basically gelling the two conditions. Being unbounded and yet having arbitrarily small elements as what is going to help us reach, right? Small elements. Okay. Probably you could state this better, but I have not thought about that. I think you can just take one of them and work with it, I guess. That should also work. But let's see if this condition is enough. Okay. Why I think is enough, because really we have had the journey, so we should be able to see that. But let's see if it actually works. Let's say you want to reach the number t. Okay. Then you can first use the elements of a1, right, to get there. So let's say to get there, meaning that of course you may not get there. So you can use this till let's say you do till ak, okay, such that ak is less than t, and then ak plus 1 is bigger than t. So of course this k is going to be unique, right? Basically you get,
Yes.
yeah, so this might, you might have seen this kind of reason. This is like an inclusion exclusion type of thing, right? In approximations. So you go A1, A2, A3, and so on till AK, right? And then you go to AK plus 1, this. Now what should be the next thing for us to reach to T? And of course, I want A1 and B1 to be disjoint. Okay. Now, why I'm putting this arbitrary condition is because I don't want to repeat the element. That was my original condition, right? But it will not really create a problem. Okay. But let's say B1 was another thing from which we could now pick things. So now what you would try to do is you would try to pick things from B1. Okay. You would try to pick things from B1 such that, and you subtract them, right? So the idea is that you subtract and you get, so that the first time you cross back and become less than t. And then you pick things from A1 and again move forward for the first time, and then you understand, right? You keep going back and forth like this. Um, is that okay? Yeah. So I am not writing it.
Yeah.
Okay. Yeah, that's fine, right? Yeah. So yes, so that is the thing. And but then what's the guarantee that you will actually converge to t? That is the problem. What is the guarantee that you will actually converge to t? Hmm. So that is because of the arbitrarily small values, right? Because see, once you move from ak to ak plus 1, let's say you have created a epsilon error, right? Next time when you move back, you carefully choose the elements from b1 which are arbitrarily small, and there's some, yeah, but yeah, this is also not going to work, right? Because again, in b1 the arbitrarily small elements may form a separate, faction, and there might be elements which are big which are making it unbounded. uh, do you see that? Yeah. So even in b1 the same problem could happen, right? So this would also not work, right? Because the arbitrarily small elements in b1 may not have enough power. Okay, so this is again not true. That's the realization. Okay, but let me fix it. Let me finally fix it. We have gone around a lot now. Okay, so really basically the idea is that the even though A1 and B1 have arbitrarily small elements, but you want the sum to be unbounded. So you will have to make sure that, yeah, so here is the condition. Okay. Yeah, here is the condition that you can actually make a so yeah, basically x3, x4, and so on, the series. Okay, or maybe I should just put it like this. You have a1 plus b1 plus a2 plus b2 plus a3 plus b3 and so on. Okay, where of course the ais are coming from a1 and the bis are coming from capital B1. Okay, and the BIs we can take to be negative. Okay, we can take the BIs to be negative. So we would want the condition that this series converges. Okay, we would want the condition that this series converges. Okay, but this series diverges, which is basically saying that the elements themselves are unbounded, right? I mean, sorry, the if you take the positive ones, then this is unbounded, but if you take the